This is a pre-recording of Chapter 4, Section 1 for Monday, March 24th, I believe, so that we can have another class presentation teaching demonstration. I want to talk about Chapter 4, Section 1, integers and divisibility. We're going to talk about dividing, and we're going to talk about the principles we want to study. Remember, we talked about even and odd and the way those related to what was divisible by what. We're doing the same thing here. I apologize for this shadow. That's the overhead light in my office. I can't really get around that. So let's talk about division. This was one of our questions on the first exam. If A is not 0 and A and B are in the set of integers, we say A divides into B evenly. That's what this vertical pipe symbol is going to be used for. That's divides into evenly. If B is equal to AC or sum C, that's an integer. So 3 divides 12 because 12 is equal to 3 times 4, and 4 is an integer. -7 divides 21, since 21 can be written as -7 times -3. And again, -3 is an integer. But 7 does not divide 15. I'll put a little slash to my symbol, since I know that to be true. 7 times 2 is 14. 7 times 3 is 21. I can't get to 15. It's in the middle. That's not going to work. So divisibility should be, I hope, something you're familiar with, whether or not you have a remainder, a leftover, or you go in evenly. So a direct question we could think of: if n and d are positive integers, then I can ask the question, how many integers in the interval up to and including n are divisible by d? It seems kind of weird to do this in the abstract, so let's do a concrete example. Let me go from 0 to 50 and ask how many are divisible by 8. Now you could start listing them all out, right? You could say, all right, I'm going to list out all the multiples of 8 until I get to something that is bigger than 50. It helps if I do my arithmetic correctly, but that's too big, so stop there. 1, 2, 3, 4, 5, 6. But if I asked the same question, how many on the interval from 0 to 500 are divisible by 8, this would not be the way I want to do it. So how can I answer this question without actually just going ahead and listing them all? Well, at this point, I'd ask you for your ideas. Pause the video, think about it for a second. I'm going to divide. If I take 50 and divide by 8, what do I get? I get 6 1/4. Hey, wait a minute, there's my 6. So if I round it down, there's my floor function. Chapter 2, section 4, that was our function. Floor, round it down. That counts. And we could think of it as, instead of just writing out the numbers that are multiples of 8, writing out all the numbers from 1 to 50 in rows that are 8 long. What's going to happen in the next row after this one? Oh, well, it's going to go 49 and 50 and then stop, and I'm not going to get to the end of the row, am I? Aha, the number of rows is what I've divided 50 into, and I round down to get rid of any fractional row. So if I wanted to do from 0 to 500, all I would have to do is take 500 and divide by 8 and round down. So what is 500 divided by 8? Well, I grab my calculator, 500 divided by 8, and I get 62.5. So when I round that down, I get 62. And if you really want to, you can go ahead and write those lists out. I don't want to. But now, how do I answer the more general question that we asked back at the beginning? Let's go scroll back up. Aha. If I'm looking at the interval from 0 to n, and I'm dividing by d, well then here's n and here's d. Here's n and here's d. So if I'm looking at the interval from 0 to n, I will take n over d and round down. Now, I didn't include 0. If I want to include 0, I need to round up instead of down, because 0 over anything is 0, and that's an integer. That works. Again, normally I would say, are there any questions here? You're not here. If you have questions, you should email me. Divisibility is a nice property. I like working with divisibility. I think it's a useful property. So let me make some claims about divisibility. Let's pick some integers. If A divides B and A divides C, then A divides their sum. If A divides B, then A divides BC for all C in the integers. If A divides B and B divides C, then A divides C. Divisibility is transitive. Now, these are all claims. If these are claims, we should be able to prove them. And the advantage is, the only thing I have about divisibility right now is our definition, which means every one of these proofs needs to use that definition in some foundational way. Now, you can prove these in any order. It doesn't particularly matter which way you want to prove them. But the proofs are all direct. So let's do one. Matter of fact, let's do one. If A divides B and A divides C, well, if A divides B, then there exists some other number, an integer. I used C, but I've got C already here. So in my definition, I'll say there exists an integer K. And then B is equal to AK. Well, A also divides C, There's another integer. I know, we'll make this K1, and we'll make this one K2. Now remember, my goal is to show that A divides C. This is a direct proof. I'm not doing anything funky. I'm not doing anything contrapositive or anything contradiction. I'm just doing a direct proof. So let's look at B plus C. Well, B plus C is AK1 plus AK2. But that's the same as A times the quantity, K1 plus K2. What do we know about that thing in the parentheses? It's the sum of integers. And if it's the sum of integers, then it's also an integer. Let's give it a name. We'll call it K3. You okay with that? Or would you rather call it something else? We can call it whatever you want. Equals A M. M equals K1 plus K2 is an element of Z. Wait a minute. B plus C is A times something where that something is an integer. Therefore, A divides that thing. Poof. Wonderful. That's exactly what I wanted to prove. B and C follow similar direct proofs. All we have to use is properties about integers and properties about multiplying and dividing. Like here, we use the distributive rule. At this point, I again would ask if you have any questions. You're not here to ask them, so I'm going to say, if you've got questions, stop the video, email me, come talk to the tutors or something. Okay. I'm going to go ahead and do 3. I'm going to skip 2. I think you should do 2, but I'm going to go ahead and do 3. 3 says if A divides B and B divides C, then A divides C. Okay. Well, let's start in the same place. If A divides B, then B is equal to A K1, where K1 is an integer. B divides C implies that C equals B K2. K2 is an integer. Okay. Remember, my goal is to show that A divides C. That means I need to look at C. But C is equal to BK2. Wait a minute. B is equal to AK1. Oh, wait a minute. I've got parentheses. I can regroup my parentheses. I can move the parentheses from around A and K1 to around K1 and K2. But K1 and K2 are both integers. Therefore, their product is, there should be a chorus of each of you in your own locations going, an integer. So this is a L. L equals K1, K2, and that's an integer. Hey, A times integer is equal to C. Therefore, C is divided, that's right, A divides into C. Exactly what we wanted. This is the transitive property in the same way that our logical hypothetical syllogism thing was a transitive property. And I like this because this helps me define the way I do division in larger cases. By the way, combining 2 and 1 together, we have a very nice corollary. If A divides B and A divides C, then A divides the quantity MB plus NC for all M and N in the integers. Well, okay, I have the multiplication, that's 2. I have the addition, that's 1, because those were the pieces we used here, right? Adding and multiplying. This is particularly useful. It's particularly useful in the methods involved in some of our next pieces. Again, at this point, I would ask a question. I would ask if there were questions, but you're not here. So I want to think about what happens when things don't divide as well. Well, then if I try and divide b by a, I get a rational number instead of an integer. But I can think of that rational number, as we did here, as an integer and then other stuff. Now, I really want to think about what happens when I divide. And I'm thinking still about integers. Quotient and remainder are going to be integers. The following is called a division algorithm, even though in and of itself it really isn't an algorithm, it's just a theorem. By the way, this dates back to Greek antiquity, so this is about 2,200 years old. If I have any integer a and a positive integer d, then there exists unique values q and r, which are integers, with a equal to dq plus r, and r is strictly less than d, but bigger than or equal to 0. If r is equal to 0, then it divides. This applies to any pair of integers, one arbitrary, one positive. Now, how does that deal with our division up here? Oh, q is the floor of a divided by d. We round down just like we did with the 50 and the 500. And the remainder is a minus q times d, or a minus the floor of a over d. This formula appears in the book on page 253. But on page 253, there's a typo. Under definition 2, page 253, they screwed up. And they just wrote the remainder is a minus d. That's wrong. So this is correct. What's in page 253 is not correct. Now, the symbols that we write for q, we write a div d. I will almost always write this in lowercase, but a lot of computer languages, when I started, forced you to use capitals, used to writing capitals. We will also write the remainder as a mod d. Now be careful, again, we'll often see this in lowercase. The textbook actually puts it in lowercase and in bold, but we don't have bold-face pen. We need to be careful here. When you use the div and the mod command, certain programming languages, when you deal with negative numbers, give you different answers. We'll do an example. Ready? I would like us to calculate 19 div 7 and 19 mod 7. Well, 19 divided by 7. I'm going to do it exactly the way we do it here. 19 divided by 7 is 2.7, round down. So I'm going to round down, and I get 2. Hello, video. My video appears to have frozen. Oh, no, my video didn't freeze. My pen froze. There we go. Wait a minute. What's left over? 0.714. What the hell is that? I don't know. So I can do this calculation. And I can say, okay, 19 mod 7 is 19 minus 2 times 7. 19 minus 14 is 5. Now that certainly works, but I think there's an easier way to do this on the calculator. So to do it on the calculator, can't see it over there, we'll put it over here. I'm going to take away the integer part of that. Now that was my remainder when I divided my fractional part. I'm going to multiply that by 7 again. There's my 5. I think that method is faster. You have to be careful. And now I would write, by the way, that 19 is 2 times 7 plus 5. dq plus r. dqr. Here's another one. 789 div 23, 789 mod 23. Out comes the calculator again. 789 divided by 23, 34 and change. So this is 34. To do the mod, again, 2 options. I can say, oh, take away the fractional part, take away the integer part, leave the fractional part, multiply back by 23. I get 7. I think that's right. Let's check it the other way and say what I want to do is 789 minus 23 times 34. 789 minus 23 times 34 is 7. I like doing the fractional version better. I think it's faster. Please note up here, A can be anything. D must be positive. If A can be anything, what's 0 div 19 and 0 mod 19? Wait a minute, I'm dividing by 19. 0 over 19 is 0. But it also has 0 left over, because 0 is 0 times 19 with 0 added. My quotient is 0, my remainder is 0. That's right. The problem comes in when A is negative. Negative 12 div 5, negative 12 mod 5. Ready? Negative 12 div 5. Negative 12 div 5 is negative 2.4. So is the answer negative 2? Wait a second. To do the div, I round down. So I go down to negative 3. If I just got rid of the fractional part, and then I tried to take the remainder, I'd get a negative remainder, and the remainder must be bigger than or equal to 0. That's why I have to round down here. So the quotient is negative 3 minus negative 3 times 5 Negative 12 plus 15 is positive 3, not negative 2. So negative 12 mod 5 is a positive number. This is where your library of choice may cause you issues. Some computer languages still use negatives in remainders. And as a matter of fact, BASIC had the command REM that treated that differently than mod. So you've got to look carefully in the library to make sure you're getting the correct modulus command that we want. And now I can say, oh, well, negative 12 is negative 3 times 5 plus 3. My remainder is a positive number. Again, at this point, questions. Pause the video, think about this, try some other examples. Page 253 and 254, examples 3 and 4 go through a number of these, and I think that's helpful. The reason I want to do this is I'm going to ask you a very simple question. What's 8 plus 5? Now, I'm sure if you're thinking the way most human beings think, you're going to say 13. Now I'm going to change this question. If I look at a clock, like the one that would normally be in my classroom, but there isn't a clock in this room, dang it. What's 5 hours after 8 a.m.? Oh, well, remember the clock only has the numbers from 1 to 12 on it. But what if I replaced this with a 0, and I started at 8 and I added 5? 8 plus 5 is equal to 1? Well, that's true because it's 1 p.m., but it's still 1. I'm going to work with remainders because really what I've done is I've said 8 plus 5, but I want to look at that mod 12 because we only go up to 12. Oh, well, that's 13. And if I say take the mod 12, I get 1. So I'm actually going to write this to mean the remainder of A after division by M. I'm working with A mod M to mean the remainder. And that means that 13 and 1 are really the same idea when I'm thinking of remainders after dividing by 12. If I have two numbers and they have the same remainder when I divide by something, M, we're going to call those numbers congruent, modulo M. We'll use a triple equal sign and we'll write mod M there. But that's the same as saying that M must divide their difference. Wait a minute, difference? I haven't done any subtraction here. Well, now I'm bringing in a new idea. So it turns out that if I think of this idea the way I want to, I can say, wait a minute here, Let's look at two numbers. 104, and then we'll go mod 24. What's 100 mod 24? I only want the remainder. 100 divided by 24, remove that part, the integer, and then multiply by 24. That's 4. Since 100 is 4 times 24, with 4 left over. Wait a minute. That means that if I did 100 minus 4, I get 4 times 24. So the modulus divides the difference of the two numbers. Aha. That's why we can use this expression for this relationship. It turns out, by the way, that you don't actually always have to deal with those two numbers directly. I could think of 128, because 100 minus 28 is 72, which is 3 times 24. So 100 is congruent to 28 mod 24. But if you're really looking at 24, both of those numbers are bigger than 24. It makes more sense to look at their remainders. 100 mod 24 we said was 4, and 28 is also 4 because 28 is 1 times 24 with 4 left over. And that's actually a theorem I can prove in general. If I have two integers and the modulus is a positive integer, then A is congruent to B mod M if and only if A mod M equals B mod M. If and only if they have the same remainders when you divide by the modulus. But just looking at this idea right here, if I looked at the difference between 128, the difference between 128 is 72. That's 3 24s. So another corollary to this A is congruent to B mod M if and only if there exists an integer k so that A is equal to B plus km. In our previous example, 100 was equal to 28 plus 3 24s. The integer was k, was 3. So that means I could think of all of the numbers that are congruent to one fixed number. I could look at the collection of numbers that are congruent to A mod M. We're going to call this the congruence class of A mod M. More on this will be coming later, but this is a really important set. usually I write this as square bracket A with an M on the outside to remind me that I'm working mod M. So if I think about 100 mod 24, well, I can use this idea to generate all of those numbers. I could add any multiple of 24. I could subtract any multiple of 24. 100 minus 24 would be 76. Subtract another 24 and you get 52. Subtract another 24, you get 28. Subtract another 24, you get 4. This set is infinite and contains numbers that differ from each other by multiples of 24. But it works for any congruence, any modulus M. And the advantage to this is that it means working with remainders actually makes my life easier. Here's another theorem. M, a positive integer, A, B, and C, and D are just regular integers. If A is congruent to B mod M, and C is congruent to D mod M, then 1, A plus C is congruent to B plus D mod M, and AC is congruent to BD mod M. So adding preserves our congruence, so does multiplying. And the reason this works is because of this idea. The proof of 1 is actually really, really short. A is congruent to B mod M. That means that A is equal to B plus some number of M's. Same thing for C and D. That should be an equal sign, not a congruence. C is equal to D plus some number of M's. So what happens when you add A and C? Well, then you get B plus K1M plus D plus K2M. Rearrange B plus D plus K1M plus K2M. Wait a minute, I'm adding things with an M in them. B plus D plus M, K1 plus K2. That's an integer. So this number is equal to this number plus some number of M's. A plus C congruent to B plus D mod M. I'm going to leave the multiplying one as an exercise for you. It might actually be in the book. Don't tell anybody. And I think if you just write out the multiplication, you'll be able to regroup exactly like this. There's a really nice result out of this. Let's suppose I wanted to do 324 times 192 mod 17. That's disgusting. So I'm not going to do it. I'm instead going to say 324 mod 17. What's that number? Oh, 324 divided by 17. Subtract off the integer part. Multiply by 17. And I get that that remainder is 1. 192 mod 17. Same deal. 192 div 17. Subtract off the integer part. 5. Well, since this is congruent to that and this is congruent to that, instead of multiplying and then figuring out the moduli, I multiply over here. And that tells me that the answer is 5. I never had to do 324 times 192. That's small enough I could. 324 times 192. Whoop, not divide. Times. That's a big number. I divide it by 17. Subtract off the integer part. Multiply by 17 again. The remainder is 5. What happened with the 0.01? Okay, round off error. I'll live. But I don't have to do the big multiplications. I can just work in the smaller numbers and work in remainders. That's incredibly useful. As a matter of fact, in general, we write A plus B mod M is actually equal to A mod M plus B mod M, all mod M. I meant to put that up here, but I ran out of room at the edge of the page. And similarly, AB mod M is equal to A mod M times B mod M mod M. So I never have to work with the big numbers. I can always work with smaller numbers. And working with smaller numbers is easier. Even in the fact that I am dealing with very, very large numbers in most computer applications, I can skip that if I want to deal with remainders. And we'll see this a lot when we do things like encryption, which is, I hope, some of what today's guest speaker is talking about as he discusses penetration testing. Because this is the beginning and basic behavior that goes into a hashing algorithm. In case you thought I wasn't being computer sciencey enough today. Again, at this point, I would ask if you had questions, but you're not here, so I can't ask you for them. I do have one more idea, and that's that I can take the clock and change it. What if I didn't want to work with a clock that only had 12? If you've done anything in military time, you work with a clock that has 24 spots in it. But you can have a clock with any number of spots in it. So I'm going to define a new idea. It's called modular arithmetic. Modular arithmetic. I'm going to define the set Zm to be the numbers that are integers up to m minus 1, including 0, but only the non-negative integers from 0 to m minus 1. I'm going to define operations in this set. A plus MB is A plus B mod M. Similar for multiplication. A times MB is AB mod M. If I'm working with the clock, then I'm doing this all mod 12. So 8 plus 5 is 1. If I'm multiplying 8 times 5, well, that's 40. And 40 is equal to 40 is equal to 3 times 12 with 4 left over. 36 and 4. So 8 times 5 is 4, but only on the clock. It doesn't matter what kind of clock you use. But I would like to point out something interesting to you. In this clock, what's 2 plus 5? Well, that's easy. That's 7. That's not any bigger. 2 times 5. Well, that's also not bigger than 12, but what's, sorry, what's 3 times 5? Well, wait a minute. 3 times 5 is 15. But 15 is 1 times 12 with 3 left over. 3 times 5 is 3. On the clock arithmetic. I'll make it even crazier for you. What's 3 times 4? If I'm working in clock arithmetic, I broke something. I broke something that was nice about multiplying and nice about adding. I added 2 positive numbers and I got 0. I multiplied 2 non-zero numbers and I got 0. Now, there are a large number of very nice properties for modular arithmetic. And there are a couple of properties that are broken in modular arithmetic. At the bottom of page 257, we start listing some of these properties. If you multiply 2 things in Zn, the answer is in Zn. The associative rules work. The commutative rules work. There's an identity. You add 0, you don't change the number. You multiply by 1, you don't change the number. There's always an additive inverse. But notice that the additive inverse of 4 is not negative 4, it's positive 8. There are no negatives in this set, so the idea of negative 4 doesn't make sense. The distributive rules work. But there are some things that are weird in modular arithmetic. And we could explore a lot of these, and we're going to look at some of them as we go forward. But the fact is that we don't always have nice things when we multiply. For those of you that are interested in this some more, there are courses in number theory that examine this in much more detail. There are also courses in abstract algebra that address this, because this is what's called a commutative ring. And rings are discussed in this course, that's SMA 310, which only a few of you are required to take, and it's a ways down the road. Okay. Again, I would be asking for questions. I hope you gave our speaker lots of attention and that you filled out the survey and that we know what you think of the teaching demonstration today. And I hope you all have a wonderful day. I will see you on Wednesday when we will cover the next section. And our exam is Friday. So I look forward to seeing you all on Wednesday. Have a wonderful rest of your day.